Welcome to Section 6, Lesson 1. In the previous 5 sections, we built every tool for working with single equations and single functions. Today, Section 6 opens with the next conceptual leap, solving multiple equations together as a system. A system of equations is a collection of two or more equations that must all hold simultaneously, and a solution to the system is a value or set of values for the variables that makes every equation in the system true at the same time. The simplest case is two linear equations in two variables, and that is where we start today. Geometrically, each equation is a line on the coordinate plane, and the solution to the system is the point or points where the lines intersect. First idea on the board: a linear system in two variables has the form ax plus by equals c paired with dx plus ey equals f, where through f are specific numbers. The system asks for the values of x and y that satisfy both equations simultaneously. Each equation alone describes a line on the plane with infinitely many solutions, but the requirement that both equations hold at once cuts the solution down to the intersection of the two lines, which is a much smaller set. Second idea: two lines on the coordinate plane can intersect in three structurally different ways. Case 1: the lines cross at exactly one point, producing a system with one unique solution. Case 2: the lines are parallel and never cross, producing a system with no solution. Case 3: the two lines are actually the same line, producing a system with infinitely many solutions because every point on the shared line satisfies both equations. The three cases correspond directly to the three possible relationships between the slopes and y-intercepts of the two lines. Third idea: to solve a linear system graphically, plot both lines on the same coordinate plane and identify any points of intersection. The intersection points, if any, are the solutions to the system. The graphical method is conceptually simple but practically limited because reading exact coordinates from a graph is hard for non-integer solutions, and very small differences between lines are hard to distinguish visually. The next several lessons cover algebraic methods, substitution and elimination, that produce exact solutions reliably regardless of the specific numerical values involved. Today we lock in the geometric interpretation and apply the graphical method to two clean examples illustrating different solution count cases. A linear system in two variables consists of two linear equations that must hold simultaneously. Each equation alone describes a line on the coordinate plane. The solution to the system is the set of all points that satisfy both equations at the same time, which geometrically is the intersection of the two lines. Here are the three possible cases. Case 1: the two lines have different slopes, so they cross at exactly one point on the plane. The system has exactly one solution, which is the unique point of intersection. This is the most common case in textbook problems and in real-world applications. Case 2: the two lines have the same slope but different y-intercepts. The lines are parallel, never cross, and the system has no solution. Algebraically, an attempt to solve the system produces a contradiction like 0 equals 5, which signals the no solution case. Case 3: the two equations describe the same line with the same slope and the same y-intercept. The lines are coincident and every point on the shared line satisfies both equations. The system has infinitely many solutions, all the points along the line. Algebraically, an attempt to solve produces an identity like 0 equals 0, which signals the infinite solutions case. Step 1 in solving a system graphically: convert each equation to slope-intercept form if not already in that form. Plot each line by identifying its y-intercept and using the slope to find a second point. Step 2: locate any intersection points by reading coordinates from the graph. Step 3: classify the case based on the count and verify by substituting any proposed solution back into both original equations. The graphical method gives an intuitive picture but is limited in precision. The next lessons will introduce algebraic methods that produce exact answers. Here is the first worked example. Solve the linear system 2x plus y equals 5 paired with x minus y equals 1 using the graphical method. Step 1. Convert both equations to slope-intercept form. The first equation solve for y, getting y equals minus 2x plus 5. Slope is negative 2, y-intercept is 5. The second equation solve for y, getting y equals x minus 1. Slope is 1, y-intercept is negative 1. Both equations are now in y equals form, ready for graphing. Step 2. Plot both lines on the coordinate plane. The first line passes through 0, 5 with slope negative 2, going down 2 units for every 1 unit right. The second line passes through 0, negative 1 with slope 1, going up 1 unit for every 1 unit right. The two lines have different slopes, so they cross at exactly 1 point. Step 3. Locate the intersection visually. The lines appear to cross at the point 2, 1. Read the coordinates from the graph A, x equals 2, y equals 1. Step 4. Verify by substituting the proposed solution into both original equations. First equation 2 times 2 plus 1 equals 4 plus 1 equals 5. Match. Second equation 2 minus 1 equals 1. Match. Both equations are satisfied by the point 2, 1, so the solution is verified. Step 5. State the solution. The system has one unique solution, x equals 2, y equals 1. Geometrically, this is the single point where the two lines cross. So the solution is x equals 2, y equals 1. The big lesson from this example is the graphical method workflow. Convert both equations to slope-intercept form, plot the two lines, locate the intersection visually, and verify by substitution. The procedure works cleanly when the intersection has integer coordinates that can be read accurately from the graph. Many textbook problems are designed with integer coordinate intersections specifically for this graphical method clarity. Real-world systems often have non-integer solutions where the graphical method becomes imprecise, and that is where the algebraic methods of the next lessons become essential. Here is the second worked example. Solve the linear system 2x plus y equals 4 paired with 2x plus y equals 7 using the graphical method. The system illustrates the no solution case where the two lines are parallel. Step 1. Convert both equations to slope-intercept form. The first equation y equals minus 2x plus 4. The second equation y equals minus 2x plus 7. Both equations have the same slope minus 2 but different y-intercepts 4 and 7. The lines are parallel because they have the same tilt but different starting heights. Step 2. Plot both lines on the coordinate plane. The first line passes through 0, 4 with slope minus 2. The second line passes through 0, 7, 3 units higher with the same slope minus 2. The two lines run parallel to each other, both tilting downward to the right at the same rate. Step 3. Locate intersections. There are none. The two lines never cross because they have the same slope and different y-intercepts. The geometric picture is two distinct parallel lines extending infinitely in both directions without ever meeting. Step 4. Conclude. The system has no solution. There is no point that satisfies both equations simultaneously, because any point that satisfies the first equation lies on the first line, and any point that satisfies the second lies on the second line, and the two lines never share a point. Step 5. Verify algebraically by attempting to solve. Subtracting the first equation from the second 0 equals 3, which is false. The contradiction signals that the system has no solution, consistent with the geometric picture of parallel lines. Step 6. State the solution. No solution. The system is called inconsistent in technical terminology, meaning the equations contradict each other, and no value pair satisfies both. So the system has no solution. The big lesson from this example is the parallel lines case. When two equations have the same slope-intercept form except for the constant term on the right, the corresponding lines are parallel and the system is inconsistent with no solution. The algebraic test, subtracting equations to produce a contradiction, is a quick way to confirm the no solution case without needing to graph. Always check for the parallel case before attempting other solution methods on a system, because the methods will produce contradictions or other failure modes that the parallel lines diagnostic identifies immediately. 3 mistakes that catch every algebra student during their first weeks of system solving work. Each one is fixable with a small explicit habit applied on every problem. First mistake: misreading the intersection coordinates from a graph due to imprecision in plotting or reading. A student plots 2 lines and reads the intersection as the point 3, 2, when the actual exact intersection is at the point 3, 3 or some other nearby integer point. The fix is to always verify the proposed solution by substituting back into both original equations. The substitution check catches off by 1 errors and any other reading mistakes immediately. Second mistake: spending time trying to solve a system that has no solution because the lines are parallel. A student graphs 2 equations with the same slope but different y-intercepts, sees the lines do not cross within the visible portion of the graph, and continues trying various algebraic manipulations to find an intersection that does not exist. The fix is to always check for the parallel case first by comparing slopes. If the slopes are equal but the y-intercepts differ, the system has no solution and you can stop immediately. Third mistake: failing to recognize that 2 equations describe the same line and treating the system as if it had a unique solution. A student looking at 2x plus 3y equals 6 and 4x plus 6y equals 12 treats them as 2 distinct equations and tries to solve, but the second equation is just twice the first, so they describe the same line. The system has infinitely many solutions, not a unique one. The fix is to check whether one equation is a multiple of the other before solving. If yes, the system is a single equation in disguise and has infinitely many solutions along the shared line. Systems of equations are the foundational tool for any problem involving multiple simultaneous constraints. Anywhere a system needs to satisfy several conditions at once, a system of equations captures the requirement and produces the solution. 4 broad sectors below. In economics, market equilibrium is defined as the price at which the quantity supplied equals the quantity demanded. The supply curve and the demand curve are typically modeled as lines on a price-quantity plane, and the equilibrium is found by solving the system of 2 linear equations representing the 2 curves. Microeconomic textbooks use this picture as the foundational tool for analyzing market behavior. In business break-even analysis, the break-even point is the unit count at which total revenue equals total cost. Total revenue and total cost are typically modeled as linear functions of units sold, and the break-even point is the solution to the system of 2 equations representing them. Pricing decisions, capacity planning, and many other business strategy questions depend on break-even calculations through systems of equations. In navigation and GPS, the position of a receiver is determined by solving a system of distance equations from multiple satellites with known positions. Each satellite provides one equation expressing the distance from the receiver to that satellite, and 3 or more such equations together pin down the receiver's 3-dimensional position. The mathematics of GPS triangulation is essentially solving a non-linear system of equations, but the linear case from today is the conceptual foundation. In engineering, the equilibrium of a structure under multiple forces is described by a system of equations expressing that the net force in each direction is 0. Statics analysis of bridges, buildings, and mechanical systems all rely on solving systems of force-balance equations. Linear systems handle the simplest cases of force-balance analysis, and the algebraic techniques you learn this week scale into the more complex matrix methods used in professional structural engineering. 3 things to take with you from this lesson today. Systems of equations are the next conceptual layer above single equations covered in section 3, and they are the foundational tool for any problem involving multiple simultaneous constraints across science, engineering, economics, business, and applied mathematics. Section 6 builds out the complete system-solving toolkit over the next 10 lessons. First, a system of equations is a collection of two or more equations that must hold simultaneously for the same variable values. The solution to the system is the set of values for the variables that makes every equation in the system true at the same exact time across all the equations together. For two linear equations in two variables, geometrically the system asks for the intersection of the two lines on the coordinate plane, which is one of three possible cases. Second, two linear equations in two variables have one of three possible solution counts depending on the geometry. One unique solution when the lines have different slopes and cross at exactly one point on the coordinate plane. No solution when the lines have the same slope but different y-intercepts and run parallel without ever meeting. Infinitely many solutions when the two equations describe the same line algebraically. The slope and intercept comparison between the two given equations diagnoses which of the three cases applies before any solving work begins. Third, the graphical method gives an intuitive picture of the system but is limited in precision when intersections have non-integer coordinates. Always verify any proposed graphical solution by substituting back into both original equations to catch reading errors. The next several lessons cover algebraic method substitution and elimination that produce exact solutions reliably regardless of how messy the numbers are. Substitution solves one equation for one variable and plugs the resulting expression into the other equation, reducing the two-variable system to a one-variable equation that the Section 3 machinery handles directly. Elimination adds or subtracts multiples of the equations to cancel one of the two variables, producing a one-variable equation the same way through a different algebraic route. Both methods produce exact answers and avoid the precision limitations of the graphical method. Together with the geometric understanding from today, they form the complete linear system toolkit. Coming up next, the lesson called Substitution Method, where we solve one equation for one variable and substitute the resulting expression into the other equation to reduce the system to a single equation in one variable. Substitution is the most universal solving technique for systems and works for any system, including non-linear ones that we will encounter later in the course. The technique is a direct application of the inverse operation skills from Section 3 combined with the function evaluation skills from Section 5 and is one of the most used algebraic techniques across science and engineering.